As with a doubly fed induction motor, a doubly fed induction generator is simply a repurposed wound rotor induction motor with a fixed frequency three-phase AC on the stator and a power electronics device known as an AC to AC converter on the rotor, which creates variable frequency three-phase AC. As with the stator, three-phase AC on the rotor creates a similarly rotating magnetic field. You'll recall in motor mode, the rotating magnetic field in the rotor locks into the stator rotating magnetic field and follows it around and around and around, exerting torque on the shaft so that it transfers rotating mechanical power to a driven load. By varying the excitation frequency and direction of the rotor rotating magnetic field, the two magnetic fields remain locked in with each other. However, the rotor is free to turn at different rotational speeds. Generator mode is essentially a repeat of the same setup with one major difference. In generator mode, some outside mechanical force known as a prime mover grabs the shaft and spins it, forcing the rotor rotating magnetic field past the stator rotating magnetic field. As it does so, exporting real electrical power to the grid. Consider an idle doubly fed induction machine with two pole pairs per phase intended to operate at 60 Hz in neither motor nor generator mode. Some outside mechanical force spins up the rotor to 1800 RPM clockwise, at which point the stator field is energized by 60 Hz. Given the rotor is turning at 1800 RPM, a synchronous speed for a two-pole pair per phase stator, the rotor is then excited with 0 Hz DC. The stationary electromagnet on the rotor locks into the rotating magnetic field in the stator, and the device starts to turn synchronously. This is a perfect setup to enter generator mode. In generator mode, some outside mechanical force, in a lab setting I'll be using a drive dynamometer, starts exerting 1.5 Newton meters torque in the clockwise direction. Given this device is synchronized with the 60 Hz grid, it can't go faster than the grid, so it remains at that same rotational speed, however starts exporting real electrical power to the grid on the order of 266 watts, with a negative sign means it's going away from the generator and into the grid. Field current is adjusted such that the generator neither absorbs nor supplies reactive power. In this condition, the generator consumes 1.5 Newton meters at 1800 RPM, or roughly 283 watts of mechanical power. To power the 0 Hz DC fixed magnetic field, the rotor consumes roughly 50 watts of power. In total, the doubly fed induction generator consumes 283 watts of mechanical power, and 50 watts of electrical power comes in, and 265 watts goes out, for a total export of 216 watts. This amounts to an efficiency of roughly 76.3%. This operating point is essentially equivalent to traditional synchronous generation, a fixed DC on the rotor, and the rotor being turned exactly at synchronous speed. If we stepped up or down field current, we could under or overexcite the rotor such that it supplies or absorbs reactive power, but let's just keep this in the balanced 0 VAR state. If we had a constant speed prime mover, we could operate like this all day. Problem is we don't. Sometimes the resource driving the prime mover likes to speed up, slow down, or take the day off entirely. Case in point, let's say there's a lull and rotor speed drops down to 1710 RPM. This is a deal breaker in traditional synchronous generators, which must be kept at a constant speed, but for DFIG, this is well inside its capabilities because the rotor electromagnet and the rotor physical position aren't tied together as with a traditional synchronous generator. Given the rotor dropped to 1710 RPM to maintain synchronous operation at sub-synchronous speeds, the rotor electromagnet needs to start rotating at 90 RPM in the same direction, such that the electromagnet appears to move at 1710 plus 90 or the desired 1800 RPM. An algebraic manipulation of the rotational speed formula demonstrates 90 RPM for a two-pole pair per phase device amounts to an excitation frequency of 3 Hz. That means that checking our work. Another application of the rotational speed formula demonstrates 1710 RPM for a two-pole pair per phase device amounts to an excitation frequency of 57 Hz. Makes sense. 3 plus 57 equals 60 Hz. Just as 1710 plus 90 equals 1800 RPM. The AC to AC converter steps up rotor excitation frequency from DC to 3 Hz AC, and the electromagnets remain synchronized at 1800 RPM. In addition to increasing excitation frequency, I should note the AC to AC converter on the rotor also steps up voltage magnitude in the same proportion, primarily because the inductive impedance of the rotor is a frequency-dependent phenomenon. If we fail to increase voltage as we raise the excitation frequency, we would eventually see field current progressively decrease and decrease an eventual underexcitation of the rotor. With increased voltage magnitude at increased excitation frequencies, field current remains inside a desired range since the generator neither supplies nor absorbs reactive power. Doubly fed induction motor lecture, available at the Big Bad Tech channel, explored the consequences of this in some detail. This demonstration will continue to make use of a linear volts per hertz profile so field current remains inside an ideal range and reactive power needs remain balanced. In this hyposynchronous condition, the prime mover still exerts 1.5 newton meters at a reduced speed of 1700 RPM, so the generator consumes reduced mechanical power input of roughly 270 watts. To power the 3 Hz rotating magnetic field, the rotor consumes an increased amount of roughly 65 watts of electrical power. This operating point still continues to export roughly 264 watts of real electrical power from the stator, where again the negative sign implies real electrical power is leaving the generator and entering the grid. In total, the doubly fed induction generator consumes 270 watts of mechanical power and 65 watts of real electrical power came in and 264 watts came out for a total export of roughly 199 watts. This amounts to an efficiency of roughly 73.7%. Let's say the prime mover slows down yet again, this time to 1620 RPM. To maintain synchronous operation at the subsynchronous speed, the rotor electromagnet needs to start rotating 180 RPM in the same direction such that the electromagnet remains the desired 1800 RPM. An algebraic manipulation of the rotational speed formula demonstrates 180 RPM for a 2-pole pair per phase device amounts to an increased excitation frequency of 6 Hz. The AC to AC converter steps up excitation frequency to 6 Hz, and the electromagnets remain synchronized at 1800 RPM. Importantly, given the inductive impedance of the rotor is a frequency-dependent phenomenon, voltage is also increased in the same proportion as excitation frequency, so field current remains inside a desired range since the generator neither absorbs nor supplies reactive power. In this hyposynchronous condition, the prime mover still exerts 1.5 newton meters at a reduced speed of 1620 RPM, so the generator consumes a reduced mechanical power input of roughly 254 watts. To power the 6 Hz rotating magnetic field, the rotor consumes an increased amount of roughly 79 watts of power. At this operating point, the stator continues to export roughly 266 watts of real power, where again the negative sign implies real electrical power is leaving the stator and entering the grid. In total, the doubly fed induction generator consumes 254 watts of mechanical power and 79 watts of real electrical power came in and 264 watts came out, for a total export of roughly 188 watts. This amounts to an efficiency of roughly 73%. After a couple rounds of this, you should get an idea of what's happening in hyposynchronous mode, i.e. below synchronous speed. If you were to draw a graph of electrical and mechanical properties as a function of rotational speed, it would look something like this. Electrical power exported by the stator remains relatively constant at around 265 watts. Note it's in negative territory, which implies it's exporting rather than consuming electrical power. Given constant torque, mechanical power consumed by the generator decreases at reduced rotational speeds. In order to keep the electromagnet synchronized, electrical power consumed by the rotor goes up at reduced rotational speeds. As a result, efficiency at reduced rotational speeds decreases. Long story short, you don't really want to run a doubly fed induction generator in hypersynchronous mode because of decreased efficiency. This being said, you still can run it at less than synchronous speeds. A traditional synchronous generator has one operating point and one operating point only, right here at synchronous speed, and you cannot run it anywhere else at all. That's the point of defig. Sure, it takes some effort and you operate at reduced efficiency, but you can keep the electromagnet synchronized at less than synchronous speed. But wait, there's more. One can also run a defig in hypersynchronous mode, i.e. at speeds above ordinary synchronous speed. Before we jump into a practical demonstration of hypersynchronous operation, take a look at the almost linear nature of these plots of rotor and stator and mechanical power below ordinarily synchronous speed. Can you draw some conclusions about what's going to happen above synchronous speed? Of particular interest is rotor electrical power. If we extend the linear slopes of these plots, the rotor electrical power plot will run straight into the x-axis and deep into negative territory. What in the hell is negative electrical power? Negative electrical power means we're exporting real power. How will this affect efficiency? Place your bets on what you think is in store, and we'll see if this is the case. Let's say the prime mover starts going to work big time and speeds up rotational speed to 1920 RPM. To maintain synchronous operation at this hypersynchronous speed, the rotor electromagnet needs to start rotating at 120 RPM backwards or counterclockwise or negative 120 RPM such the electromagnet remains the desired 1800 RPM. An algebraic manipulation of the rotational speed formula demonstrates 120 RPM for a 2-pole pair per phase device amounts to an excitation frequency of 4 Hz. Since it needs to go counterclockwise, let's call this negative 4 Hz. The AC to AC converter changes excitation frequency to -4 Hz, and the rotor and stator electromagnets remain synchronized at 1800 RPM. Importantly, voltage is also proportionally increased, so field current remains inside a desired range, such that the generator neither supplies nor absorbs reactive power. In this hypersynchronous condition, the prime mover still exerts 1.5 Newton meters at an increased rotational speed of 1920 RPM, so the generator consumes increased mechanical power input of roughly 302 watts. To power the -4 Hz rotating magnetic field, the rotor consumes a decreased amount of roughly 36 watts of power. This operating point still exports roughly 266 watts of real electrical power, where again the negative sign implies real electrical power is leaving the stator and entering the grid. In total, the doubly fed induction generator consumes 302 watts of mechanical power, and 36 watts of real electrical power came into the rotor, and 264 watts came out of the stator, for a total export of roughly 228 watts. This amounts to an efficiency of roughly 75.5%. That's just the beginning. The prime mover again ramps up rotational speed, this time to 2040 RPM. To maintain synchronous operation at this hypersynchronous speed, the rotor electromagnet now needs to rotate at 240 RPM backwards or counterclockwise, such that the electromagnets remain synchronized at the desired 1800 RPM. An algebraic manipulation of the rotational speed formula demonstrates 240 RPM for a two-pole pair per phase device amounts to an excitation frequency of 8 Hz. Since it needs to go counterclockwise, let's call this -8 Hz. The AC to AC converter changes excitation frequency to -8 Hz, and the rotor and stator electromagnets remain synchronized at 1800 RPM. Importantly, voltage is also proportionally increased, so field current remains inside a desired range, so that the generator neither supplies nor absorbs reactive power. In this hypersynchronous condition, the prime mover still exerts 1.5 Newton meters at an increased rotational speed of 2040 RPM, so the generator consumes an increased amount of mechanical power of roughly 320 watts. Powering the -8 Hz rotating magnetic field necessitates the rotor consumes a decreased amount of roughly 17 watts of real electrical power. The stator continues to export roughly 268 watts of real electrical power, where again the negative sign implies real electrical power is leaving the generator and entering the grid. In total, the doubly fed induction generator consumes 320 watts of mechanical power, and 17 watts of real electrical power came into the rotor, and 260 watts came out of the stator, for a total export of roughly 250 watts. This amounts to an efficiency of roughly 78.4%. If we revisit our earlier graphs of electrical and mechanical properties as a function of rotational speed extended into hypersynchronous mode, you shouldn't be surprised. Electrical power exported by the stator remains relatively constant. After all, the stator is blissfully unaware that anything has changed, and it still sees an electromagnet pass it at regular 1800 RPM despite elevated rotor speed. Given constant torque, mechanical power consumed by the generator increases at increased rotational speeds. Electrical power consumed by the rotor continues to go down at increased rotational speeds. We're not in negative territory yet, but it does seem like the job of keeping the two electromagnets aligned does get easier and easier at increased rotational speeds. As a result, efficiency increases at increased rotational speeds. Long story short, this is where you want to run a doubly fed induction generator. Not only is the hypersynchronous range unavailable to traditional synchronous generators, which have one operating point and one operating point only, it's also more efficient than traditional operation. This is like a double bonus round. But wait, that's not all. If the prime mover is capable of exerting enough mechanical power to further accelerate the rotor, one of two things is going to happen. One, nothing. Yeah, kind of a buzzkill, but sometimes nothing cool happens. Or two, something super cool happens. The electrical power consumed in the rotor will eventually go negative, and we can start extracting power from both the rotor and the stator. This is where we enter the triple secret bonus round. Allow me to differentiate between these two paths. Without taking the AC to AC converter entirely apart and taking those parts into smaller and smaller parts, which might necessitate a 22-week-long discussion of semiconductor devices and circuits power electronics, one can simplify the AC to AC converter as an AC to DC converter, a rectifier, hooked back-to-back with a DC to AC converter, an inverter. Up to this point, we'd be using the AC to AC converter in one direction only, where it accepts incoming three-phase AC with a fixed voltage magnitude and frequency from the source, rectifies it all to DC, then inverts this DC to three-phase AC with user-adjustable magnitude and frequency, and then sends it to the rotor. If we use a traditional unidirectional AC to AC converter intended for one-way operation, source to rotor only, this essentially kills the possibility of exporting power from the rotor to the source because it's not designed to operate backwards. If, however, you do have a bidirectional AC to AC converter or are very comfortable infringing upon General Electric's numerous patents for bidirectional AC to AC converters, the moment the rotor power goes negative, the AC to AC converter rectifies it, inverts it, and sends it back to the source. Compare and contrast a doubly fed induction generator with a bidirectional AC to AC converter on the rotor only with our earlier diagram of a traditional electrically excited or even a permanent magnet synchronous generator with full conversion. For obvious reasons, doubly fed induction generator with a bidirectional AC to AC converter on the rotor is sometimes referred to as partial conversion. While both systems do allow for electrical power generation at different rotational speeds, defig with partial conversion is substantially cheaper than synchronous generation with full conversion because those power electronics on the rotor don't need to be sized to handle all the power transfer all the time. Assuming we have this bidirectional capacity, we might extend the plots of electrical and mechanical properties of the function of rotational speed as follows. As rotational speed continues to decrease, electrical power exported by the stator should remain relatively constant. Given constant torque, mechanical power consumed by the generator continues to increase at increased rotational speeds. Of interest, electrical power consumed by the rotor eventually crosses zero and goes negative, implying the rotor also exports real power. Total power exported by the doubly fed induction generator is additive, given the rotor and stator have the same polarity. Here's a couple sample data points where I've extrapolated the rotor data as if I was using a bidirectional AC to AC converter. At 2160 RPM, the AC to AC converter supplies negative 12 Hz to the rotor such that it revolves at 360 RPM counterclockwise and the electromagnets remain synchronized at 1800 RPM. Mechanical power input increases to roughly 339 watts. The stator continues to export roughly 269 watts, only this time the rotor also exports 5 watts. 339 watts of mechanical power went in, and 269 plus 5, or 274 watts of real electrical power came out. This yields an efficiency of roughly 80.8%. At 2280 RPM, the AC to AC converter supplies negative 16 Hz to the rotor, such that it revolves at 480 RPM counterclockwise, and the electromagnets remain synchronized at 1800 RPM. Mechanical power input increases to roughly 358 watts. The stator continues to export roughly 266 watts, and the rotor exports an increased amount of 24 watts. 358 watts of mechanical power went in, and 266 plus 24, or 290 watts went out. It yields an increased efficiency of roughly 81%. Long story short, given we're exporting power from both the rotor and the stator at higher and higher hypersynchronous speeds, efficiency continues to increase. This is where you want to run a doubly fed induction generator. Not only is it expanding the range of traditional synchronous generation above synchronous speed, it's also more efficient. Now, before you get too excited, realize you can't expect efficiency to keep climbing forever, and this does have its limits. Last, I wanted to share with you a quick visual that may assist you if the graphs aren't doing its tricks. One of the lab manuals I use has the students draw arrows illustrating power flow for synchronous, hyposynchronous, and hypersynchronous operation. It might seem hokey, but I found this actually helps certain students really visualize what's happening. In the synchronous condition, a certain amount of mechanical power is consumed by the generator. Establishing the fixed DC field in the rotor necessitates the consumption of a certain amount of real electrical power. In this synchronous state, the stator exports an amount of real power. As a result, the total quantity of real electrical power is exported for use. In hyposynchronous conditions, the rotor still exerts the same torque but at a reduced rotational speed. As a result, mechanical power input decreases. Establishing a rotating magnetic field in the rotor to make up the difference necessitates the consumption of more real electrical power. In this hyposynchronous state, the stator exports roughly the same amount of real electrical power. As a result, a reduced total quantity of real electrical power is exported for use. In hypersynchronous conditions, the rotor is still exerting the same torque, but at an increased rotational speed. As a result, mechanical power input increases. Establishing a rotating magnetic field in the rotor necessitates the consumption of less real electrical power. In this hypersynchronous state, the stator exports roughly the same amount of real power. As a result, an increased total quantity of real electrical power is exported for use. Above a certain hypersynchronous speed, and with the bidirectional AC to AC converter, mechanical power continues to decrease, and the rotor eventually starts exporting real power. As a result, an increased total quantity of real electrical power is exported for use. Lastly, despite the simplified explanation of defig featured in this lecture, don't for a moment think defig is easy. Think about all the incoming data the control system needs to simultaneously keep track of and manage to ensure the generation process works at all, let alone efficiently. Obviously, a control system needs to keep track of rotational speed and quickly respond to any variances by increasing or decreasing rotor excitation frequency to keep the two electromagnets synchronized. As if this wasn't challenging enough, changes in excitation frequency also necessitate simultaneous changes in voltage because of changing inductive impedance, so field current remains inside a desired range such that instantaneous reactive power requirements can be met. Add to these electrical complexities the management of mechanical actuators that control blade pitch used to regulate mechanical power input. Add to the electrical and mechanical complexities manufacturer-specific management schemes like vector control, direct torque control, and low-voltage ride-through. For these recognizable reasons, DFIG is sometimes referred to as DFIG-PFM, doubly fed induction generation pure fine magic. This being said, despite the complexities of real-time management, DFIG ultimately is synchronous generation, only it occurs at variable speeds, principally because the rotor's physical position and the electromagnet are not tied together. In hyposynchronous operation, the rotor electromagnet can be turned in the same direction as the underspeed rotor to make up the difference. Whereas in hypersynchronous operation, the rotor electromagnet can be turned in the opposite direction of the overspeed rotor to slow it down. In either scenario, the stator is none the wiser and continues operating as if an electromagnet maintains synchronous speed. The sheer cunningness of this trickery never ceases to amaze and impress me. In conclusion, we compared and contrasted the benefits and drawbacks of traditional synchronous generators with induction generators and discussed how DFIG is an ideal third option which can both operate at variable rotational speeds and manage reactive power requirements. We learned in hyposynchronous operation, the rotor electromagnet can be turned in the same direction as the underspeed rotor to make up the difference. And in hypersynchronous operation, the rotor electromagnet can be turned in the opposite direction of the overspeed rotor to slow it down. Additionally, we examined plots of DFIG electrical and mechanical properties at different rotational speeds and explored the use of a bidirectional AC to AC converter to extract power from the rotor. Lastly, we compared and contrasted synchronous generators making use of full converters with DFIGs making use of comparatively less expensive partial converters. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.